Welcome back. And here's disaccharides you absolutely must know for test 4. There's a lot in common that all these have. Glucose is involved in some way in every one of these. So glucose, there's 2 glucoses being used to make alpha or beta cellobiose. The mixture of alpha and beta cellobiose is depicted here. Mixture of alpha and beta. Glucose is responsible for making half of sucrose. That's the stuff you put on your breakfast cereal or in your tea or coffee or whatever you put sugar in, because that's your table sugar. There's glucose involved in lactose over here. In fact, look at how similar the alpha beta lactose mixture is to the, let's just look at this version of cellobiose. What's the only difference between these two? Well, it looks like the 4th carbon here, carbon 1, 2, 3, 4. Nope, don't want to do that. Carbon 4 of galactose has an up OH, and carbon 4 of a glucose, the same OH is down. So they are diastereomers of each other. And that's the only difference between those two. The linkage is the same. It has to be, is that alpha or beta? It's alpha. This has nothing to do with the name here because it's also alpha in this one, where this thing is beta up here. So the thing that makes this beta cellobiose is, okay, beta cellobiose is right here. The thing that makes this alpha cellobiose is here. The thing that makes them both cellobiose is 2 glucoses hooked up with a beta linkage to each other. So cellobiose has to have a beta linkage. Beta linkage. Cellobiose has to be beta here and beta here. That's what makes you cellobiose. Now, if the beta linkage is between galactose and glucose, it's beta, but it's not glucose on the left side this time. It is galactose. And then you're talking about lactose. And there's a lot of people that have trouble digesting lactose, and there's every person on the planet has trouble digesting cellobiose because, as its name suggests, it is a broken down product of cellulose. Look at the spelling, starts off with the same 4 letters, and people cannot digest wood. Cellulose breaks down to these smaller molecules. Can't digest that. And it's that beta linkage that gives us digestion problems. So here's another beta linkage, gives a lot of people digestion problems, but there's an enzyme that most people have called lactase, ASE, at the end that will break down this to 2 useful sugars that you can use for nutrition from your mother's milk, because that's where you find lactose. Okay, sucrose. It's the only one on this page where both anomeric carbons are acetals. This is the only non-reducing sugar on this page. All these other comments say reducing sugar, reducing sugar, reducing sugar. Why? Hemiacetal, hemiacetal, hemiacetal. No hemis, no reducing sugars. And the acetals between the anomeric carbon of glucose, which is carbon number 1, and the anomeric carbon of fructose, which is 2 because it's a ketose. Carbon 1 is over here. 2 anomeric, it's an acetal. OC, COC, and COC, geminal diether. And that's between glucose and fructose. The linkage on the glucose is alpha because these are trans. The linkage on the glucose is beta because these are cis. And that is summarized here. The linkage from glucose is alpha. The linkage from fructose is beta. And that's the linkage describing the two. And what else we got? We have maltose. Now everybody can digest maltose, and it, like cellobiose, is a mixture of two glucoses, except everybody can digest glucoses when they're hooked up in an alpha fashion. All right. Alpha is digestible between when you have two glucoses. And beta between two glucoses, undigestible. Just the direction of that bond says that it'll fit in the enzyme for digestion here, and it won't even go close to the enzyme here. So do you have to know how to draw these on a test? Yes. Over here is a typical test question that will show up on your test 4 as well. If I don't say anything here, it's based on Winter 19. This is a Winter 19 exam question. You'll see, you just change exams. It changes maltose to cellobiose to sucrose to, what's the fourth one? Lactose. You'll have one of those 4 right up there. And I want you to draw the beta version of maltose. So what do you have to remember about maltose? That's the one with 2 glucoses. Digestible version with 2 glucoses. So the glucoses are alpha 1,4. And here's how I remember. You could go through all the steps with the icon, et cetera, et cetera, et cetera. Or you could remember that glucose is, there's a reason why it's the #1 monosaccharide in all of nature. And it's based on stability. Because except for the anomeric position, everything is equatorial in glucose. Equatorial. You might want to review how to draw chairs, because this saves you from remembering ups and downs. There you go. Up, down, up, down. And hey, it's maltose, which means we need to have, what kind of linkage? Alpha or beta? For digestion, it needs to be alpha. And you're saying, wait, it says beta, Dr. Whitaker. No. That's the anomeric position, where it can be a mixture of alpha and beta. To be maltose, you have to have glucoses hooked up alpha to each other from carbon #1 of the 1 glucose to carbon #4, 1, 2, 3, 4. So copy another one of these. And that O is the red O in the other one. So let's see, I need a carbon that's a little above the O right there in a chair. It's glucose, everything's equatorial. I'll worry about that beta cellobiose in a second. Beta cellobiose, beta maltose. What did I say cellobiose? I don't know why I said cellobiose. Beta maltose means the anomeric OH that I'm about to draw has to be cis to the CH2OH right here. That means it'll be up. I'll put it in pink. If it was down, the name of the molecule would be alpha maltose. Good. This is an O here. And then copper sulfate is Benedict's. We're buffering it to a high pH, so we're going to get a carboxylate. Where are you going to get a carboxylate? Will it be at the acetal position? Answer, no, you don't get reactions at the acetal position. You get reactions at the hemiacetal position. So here's what I'm going to do. I don't want to redraw things that I don't have to. So this guy out here does not change. So R is bonded to this, comes to a CH2OH. And this used to be connected in the ring, but it's been liberated when it went to the open form. Remember, these are in equilibrium with the open form, and that's what reacts. And we got this, goes to an OH. Doesn't have to look pretty anymore. It's not like we're shooting for a chair. Buffered to pH 11, you don't draw a carboxylic acid there, you draw a carboxylate. And there. And what's an aldonic acid? Here's what I'm going to do. Aldonic acid is the one where the top carbon, which is the open chain carbon here, needs to become a carboxylic acid. So do another circle. New color. Green. Use green. Pink. Everything up to, but not including that. And here, monouronic acid means only one of the saccharides was converted to a uronic acid. You pick one. Remember, uronic acids have this CH2. This used to be the one on the bottom of the Fisher. That one can be a carboxylic acid, or this one, and it says I want one of them here. So I can keep my theme of the blue R here and not do that one. R is attached to this. And we do want to draw the ring and everything. Oh, that's terrible. Haste makes waste. There. And not touching that. Not touching this. Not touching that. Gotta touch this though. It really doesn't like me doing O's too fast, does it? Okay. So, not big points, but there's a few points there. 6 points for knowing our disaccharides. I think you really want to know your disaccharides. And next up, we'll do a lecture on things you may have heard about in your biology class, nucleosides and nucleotides. Nucleoside, nucleotide. They both have ribose. Or 2-deoxyribose. This would have a D in front of its name. Has D in front. Like DA. That's deoxyadenosine. Draw DA. We'll do that eventually. And we'll do diphosphate as our final exercise on this page. Okay. So depending on the name, we'll be using ribose or deoxyribose. And they're so common that we have to just, I don't want you going to the front page of the exam to figure out ribose ends up looking like this. Down right, down right. That's optional. That's carbon 2. I'm going to put R. R equals OH in ribose. I don't know where di came from. In ribose, R-I-B. Or I'm saying things and intending on writing what I say, and it's not happening today. Got too much going on today. Or R equals H in deoxyribose. I know where those D's were coming from now. Okay, this will always be an N. And I got a circle around it because N in a ring. And that'll be one of the nitrogenous bases. One of the nitrogenous bases. A, C, G, T, U. Adenine, cytosine, guanine, thymine, uridine. And over here, always have this and R prime. R prime equals phosphorus in nucleotides. Here's the difference to nucleotides. R prime equals H. So that's an alcohol up there in nucleosides. So that's all you need to know there. Okay, I'm going to steal the nitrogenous bases from page 1 and tell you which ones are, which positions of them are the N that actually attaches to the ring. We have to know that because the teacher's not going to tell you on test day. And the handout doesn't tell you ever which of the N's ends up attached to the sugar, the ribose. There's a lot of N's here. I think we were here. And squeeze it in over here. Shrink it a little. Sure. So a highlighted N ends up in the ring is what I'm going to do over here. Highlighted, not in the ring. Highlighted N ends up on ribose. So that's the N I drew with the circle around it here. This N highlighted. And over here, it's this one. And over here, it's this one. So you're seeing things they all have in common yet? Not this one, but this one. And don't say it's the only one that's an NH. You're in trouble. You got two other NHs, one other here, and you got another one here. Well, if you have a ring size 5, which NH is it? It's the one in ring size 5 that has an H on it. Don't pick the one without the H. You're going to lose a point. You use the wrong N, it doesn't attach. Ring size 5, use the NH in the ring. Ring size 6, what do these both have in common? Amide. Knowing your functional groups really helps. Use the amide N in ring size. How about this? In, what do you call the rings where there's There's only one ring, and what do you call the two where there's two rings? Once again, these are called pyrimidines. And these two are called purines. Use the NH in ring size 5 for the purines. In pyrimidines, they have the bigger name because they come from the smaller rings. That's how I remembered it. And you're saying, wait, this is an amide too, Dr. Whitaker. And I say, no, it is not. This over here is an imide. Do not use an imide nitrogen. Do not use this nitrogen. It's an amide nitrogen, but it doesn't have an H. Amide NH. How's that? That H will be disappearing during the condensation reaction. Notice there's no H on this end here. There's a ring, clearly. And how are we doing? I think we can do our example before our break. Test example, boom. You will have this question on your test. Not this exact one, but I'll just change these 3 variables. And I'm not compelled to obey the laws of nature. I have a mixture of deoxyribose, and normal ribose in this molecule. That doesn't happen in nature. But I did tell you what the D means. Carbon 2 of ribose will not have an oxygen here, will not have an oxygen here, and there's no D here, so you need the oxygen there. So as soon as you show up and see this question on the test, I will I will show you how to get 3 of the points without even finishing reading the question. You say, oh, this is a trinucleotide. You know how I know? Well, the question says so. That's one way to know. See a trinucleotide? You have to draw the minimum. Min in green for any trinucleotide. So here we go. We got the ribose. This is ribose number 1. This position is never missing an O. There's always an O here. There's always an N here. Don't finish it, but there's always an N there. There's not always something here, so I'm just leaving it blank for now. And there's not an OH here either. It's an O phosphate, because one thing I didn't tell you, but your biology teachers told you, I'm pretty sure at one time, there's a phosphodiester backbone to hold these linkages together. Does that ring a bell for anybody? And you guys actually know how to draw phosphate esters. There's a ester of phosphoric acid. It needs to be a diester. And this O here on the right connects to carbon 5 of the other ribose. And we got another phosphodiester here. So no matter what trinucleotide I'm making you draw, you're drawing this as a minimum for any of them. And you need an N always here and here. And don't try to find out what happens if you draw the N like this. Here, I've had students do this. They don't remember if it's pointing up or down. Well, that's important to know if it's up or down. So if they draw it straight across, half point off. You didn't show me it has to be beta, or else it's not a real molecule. Even after the teacher confessed this isn't a real molecule to start with. But I want you to draw it as if it was. Okay, so the minimum's there. I'm going to sneak back here because we have some information I'm going to re-steal. Yeah, let's see what I can get away with here. I'm going to get some arrows and things that I didn't want. We can get rid of the extraneous stuff here. X. I need that stuff. Those highlights won't be on your handout. And if they're on your handout, I'm going to be very mad at you. Because on test day, yes, you can have a printout version of that handout, but I don't want any writing on it. I want it to be the original clean handout. Okay, you can highlight those after the exam starts if you want. All right, so I want to be able to see the question. All right, DT. That's funny. That's my initials. DT. T. I need the T. Where's the T? Oh, thymine has R equals CH3. So please don't draw R here for me. Put a CH3. End of a stick is fine. Connect that nitrogen. That is the green nitrogen right here. T. We'll do it in blue because the minimum part's over. And here's how I look at it, because this thing needs to be rotated around. The N is connected to a carbonyl, is connected to an NH. The N is connected to a carbonyl, is connected to an NH. The NH is then connected to another carbonyl, connected to a carbon with a methyl. Connected to a carbonyl, connected to a carbon with a methyl. The carbon with a methyl is double bonded to another carbon, which comes back to the N. Double bond to another carbon, which comes back to the N. See how I did that? Doesn't have to look great. That's got everything in the right order around the ring. And DT means I don't want an O here. DC means I don't want the O here, but there's no D on the G, so I am putting the OH down here on position number 2. Going back and finding the C, which means I'm going to connect this highlighted nitrogen, that is this nitrogen here. It comes to a carbonyl and then goes to an N. Comes to a carbonyl and goes to an N. The N is double bonded to a carbon that has an NH2 outside the ring. Double bond to a carbon that goes to an NH2 outside the ring. Single bond to a carbon that's double bonded to another carbon. Single bond to a carbon, double bond to another carbon. That carbon comes back to the N. And there we are. I got everything. Yeah, beautiful. And then I want my G. There's the G, N, single bond to a carbon, double bond to a nitrogen. Single bond to a carbon, double bonded to a nitrogen. Finish the first ring first. Double bonded nitrogen goes to a carbon, double bond to carbon, comes back to the ring. Goes to a carbon, double bonded to carbon, comes back to the N in the ring. All right, where are we at now? We came back. Now we got from the, let's see, proximal to the N that's green. That's the N that's green, right? We go new ring, N, double bond C. New ring, N, double bond C. The C has an NH2 sticking off the ring. And the C also has a bond to NH. The same C has a bond to NH. And then the NH is bonded to a carbonyl, which closes back up to the first ring. And there you go. And then we follow the instructions here. Oh, there's lots to know, huh? We have, oh, there was a typo, and I can't remember which part I fixed on the answer key. These both can't be 5'. One of them has to be 3'. I'm just saying. I can edit it here. You guys are smart enough. You can figure out, oh, he changed the other one the other time. I'll make that the 3' end. Ugh. And you have to remember the numbering on the rings is the anomeric one is 1, 2 is the one where it could have deoxy or not. 3 is there. 4 is here. 5 is there. And the 5' end has a free hydroxyl. It's called the 5' end. There's a reason why I'm not going to put primes on all these. 5' end, and the 3' is over here. It's the part that's not part of the backbone. It's the ends. 5' end is always first. The convention is to go 5' to 3' when you're doing the sequence, okay? So that's a new thing. The order is always 5' goes to 3'. So that'll be the 5' end, and the last one down here has the 3' end, and there's the 3' here. And we'll circle things gently. Free hydroxyl, 5' end, and triphosphate on the 3' end. And that's this one. And yeah, you have to know how to draw triphosphoric acid. We started doing this a long time ago. Remember, it's an anhydride of more than one phosphoric acid. And in this case, because it's a TP, a triphosphate, sorry, which is TP, short form, you need 3 phosphoruses linked up as anhydrides with each other. Okay, triphosphate. If it's a diphosphate, it would stop right here. If it was a monophosphate, it would stop right here. Boom. That's your options. Yep. I'll have them. I could have phosphates on both ends. They'd be mono, di, or tri. So there's lots of possibilities here. So I expect everybody to get perfect on this question. There's no reason not to. And then I always make you do hydrolysis reactions. First, you do an acid hydrolysis, and then you buffer it to pH 6.5. And I'm seeing who's paying attention here. I gave you the pKa's of phosphoric acid. Here's a sentence I'm going to put here that should be good for all of organic chemistry, and just take it to the bank for any future course involving acids and bases. If the pH of the environment is above the pKa for an acid, then the acid is in its deprotonated form. Remember, a high pH means basic, right? So if the environment is basic, then you take the H off. And we're going to make this very big. We're going to copy the whole thing and flip the script. If the pH of the environment is below the pKa for an acid, then the acid, wow, you know, I think this is an ACES computer thing. Not every time you hit the space bar does it take. Are you with me on that? Some ACES owners out there? Or is it just me? Then an acid will be protonated. If the pKa, if the environment is acidic, doesn't it make sense things will be deprotonated in basic conditions and protonated in acidic conditions? Doesn't it sound like this is real important? Needs to be red, needs to be bold, needs to be, I don't know, 24-point font. This will be the last thing we mentioned before a little break. Yeah. Let's see. Yeah. We'll fix it. So you read those and you get ready to fill in these boxes because you're going to hydrolyze all the groups except for the groups in the rings. These rings are aromatic and stable, so they don't break open the rings. But you're going to hydrolyze your N-acetals. You're going to hydrolyze phosphate esters. And what else? And you're going to hydrolyze this phosphate ester, and the triphosphate is going to end up hydrolyzed as well. And then you're going to use these sentences here. And when you draw phosphoric acid, you're going to have it, let's see, we're doing this at pH what? 6.5, which is above this number, deprotonated. Below this number, you'll be protonated. Below this number, protonated. Every one of your phosphoric acids will be diprotonated. You'll have one H missing. And there will be how many of them? 1, 2, 3, 4, 5. 5 of them over there. Big clue. Coming back in a few minutes for our short finish. And I'll see you then.